It's a pleasure for me to introduce Karim Thébault from Bristol, also work together with Huggett. Unfortunately, he couldn't make it, but he's somehow in the presentation on the emergence of temporal structure in Wheeler-DeWitt Cosmology. Thanks, many thanks, Karim, for coming. It's really nice to see you here. So, wherever you want.
Thanks, Christian, and thanks to Olympia as well for the organisation. It's really wonderful to be in Argentina. I'm just trying to find somewhere to stand that I don't get blinded. So just before I actually start the talk, I hope the organisers will forgive me for doing a little bit of advertising for the Philosophy of Physics Society, which was created not so long ago. Please join the society. It's free if you're a student. It's extremely cheap if you don't have your university funding to pay for it. Please, if even the low rates are too high, just send an email to the society, and usually we can waive the fees if needs be. All the money from the society, as it stands, goes into supporting a new journal edited by David, which is up and running, open for submissions, called Philosophy of Physics, which I thought was quite a nice title. So please, if you go on the website, it's all the details here. It's just philosophyofphysics.org. You can read more about the society in the journal, and please do submit your best work and join the society. Okay, right, to the talk. So this joint work with Nick Huggett, we were very lucky to have Nick in Bristol for a few months at the end of last year. And it's really focusing on a particular kind of model of Wheeler-DeWitt cosmology, a very simple model. And it's part of partly thanks to the John Templeton Foundation as well for supporting a project I'm working on the arrow of time, which is, this work is kind of related to. I'll say a bit more about that later maybe. Okay, so this is really a case study. We just want to look at a specific detailed model which putatively shows the emergence of time. And we want to look at the kind of explicit equations and try to look at a kind of exemplar of what it might mean for time to emerge from a context in which there isn't time fundamentally. It's particularly interesting in the philosophy literature, some criticisms of this style for the derivation of the consistency, which makes it, I think, more exciting, more interesting to look at. We're going to look at some criticisms from, I'm going to mispronounce his name, Chua and Craig, the paper from 2012? Sorry, 2022? Anyway, very recent paper. And also some much older criticisms about a general style of argument from Hugh Price that he made in the context of the no boundary proposal, but are interesting for this context as well, particularly because there's formal similarities to the context that Hawken applied the no boundary proposal and the models that I'll be talking about. And we're going to argue that there is a self-consistent account of emergence of three types of temporal structure, which I'll call chronoordinal, chronometric, and chronodirected. I'll say what that means in a few seconds. And at least with respect to the first two structures, there's some kind of explanatory value of the emergence of the derivation. So first, just a little bit of conceptual housekeeping. I think perhaps this will also help a bit with the overall theme and discussion of the conference, just to distinguish what we mean by time or temporal structure. In particular, because I think it's important to differentiate between ordered structure and directed structure. So we can call these grades of temporal structure. I apologize for my slightly eccentric naming of them. I just thought it'd be quite nice to have some symmetry. Chronometric structure, you're probably familiar with the idea. If you kind of expand the same kind of naming convention, you could think about chronoordinal structure, temporal ordering structure, and chronodirected structure, temporal directed structure. And these, in some ways, are overlapping. You can define them based upon each other, but they're formally distinct structures you can define within a theory. Some of this work is actually from a book which I'm working on with Sean Gribb, which will hopefully come out later this year. And it's kind of the framework which we're embedding into a quite large, bigger story about how to analyze structure and symmetry in physical theory. So what are these structures? This chronoordinal structure is essentially what McTaggart meant by the C series. There's some really nice work by Matt Farr on looking at the C series. Really what we're talking about is a representation of time ordering of sets of events that isn't directed. So we don't have a before-after relation. We can organize events in an undirected temporal line. So given 3 events in the domain of the structure, we can specify whether A and B and C, whether B is between A and C, but we don't have a specification about whether which is after which. So it's a thinner structure than a directed temporal structure. It's just ordinal. Chronometric structure is the one probably in terms of its name more familiar. Essentially, we've got a kind of a structure that gives a representation of temporal distances. It may not be a complete assignment, but we get some kind of real valued assignment of duration between events or groups of events. And usually we can use this to actually implicitly define chronoordinal structure, given that we have a kind of real numbered valuation that can be negative. So we can use this to pick out ordering that's undirected, in fact, as well. And then finally, and really the focus of the workshop, and I think it's interesting the sense to which you can have this structure but with a monotonically increasing function and call that an arrow of time. Or you have this thicker structure where you genuinely pick out a direction of time. So you have directed time orderings of events, we have a directed temporal line, and given 3 events in the domain of the structure, we can define a before and after relation. And often you can define this from a chronoordinal structure plus some specification of a temporal orientation. So what are we interested in? We're interested in a particular context where we have a set of dynamical equations and the structure in question is not present in the explicit form of the original equations we're given. And these will be Wheeler-DeWitt type equations in the model we consider. There's then some formal derivation of one or more of the structures that I mentioned in some limit or with some approximation or both. So the structure isn't in the original equation explicitly, but we can kind of implicitly find it within some limit. The question then is the sense in which the formal derivation is physically salient and explanatory explains why the relevant temporal structure obtains or approximately obtains in some limit, which is usually going to be something like a low energy or semi-classical regime. So this is the kind of story about the emergence of time from an equation which doesn't have time. We're going to specifically map it into the derivation of these structures approximately that can play the kind of role of time in the limited theory or in the semi-classical regime. And I think this is a kind of fairly common view in physics to think about emergence in this way of derivation under approximation. It's becoming more popular in philosophy. And it maps up with work that Nick's done, I mean, quite extensively over many years with Chris Vutric. And I hope Chris will forgive me. I put a positive, speculative date that hopefully their book will come out soon. I know it's not actually finished, but I'm looking forward to reading it. So let's hope this date is true. And so the particular model I want to talk about is work, I mean, really mostly by Klaus Kiefer across many papers and his book, which is I think in its 3rd or 4th edition, but also a particular kind of part of Kiefer's work, which was done with Zeh, and there's a specific paper that I'll talk a little bit about the results that they did from 1995. I'm sorry that the referencing, I haven't actually got proper reference slides at the end. If you do email me, I can send you any of the references with the further details if you like. I believe their paper is called The Arrow of Time in a Recollapsing Universe. So we then look at the objections to this stories in terms of the explanatory nature and the physical salience of the derivations. That's the kind of roadmap of what we're going to do. The story about how we get to the Wheeler-DeWitt equation a little bit first, and I'm really not going to tell the story in any detail because we'll be here for some time. But it really kind of most of it starts with this man. Does everyone know who this is? I actually couldn't find a picture of Dirac during the relevant period somehow. I mean, it's quite difficult. He's a bit old here. I think this is from the mid-60s. But really, it's kind of I mean, for someone as appreciated as Dirac, it's kind of amazing to say he's underappreciated, but he really did fantastic work from the late 40s and particularly in the 50s to derive a kind of incredible framework for constrained Hamiltonian dynamics, apply it to general relativity, and construct an algorithm for doing quantization, which at the time was not particularly rigorous, but has now been fleshed out into a kind of more solid foundation. So there's a huge kind of body of work that Dirac did in this period, which was after the period he's kind of more famous for. Ultimately, the kind of really important part of the story for what we're going to talk about happens later, and which Dirac had to some extent ambivalent relationship with, is that once you have this procedure for deriving turning a theory into a constrained Hamiltonian theory and then turning that constrained Hamiltonian theory into a quantum theory, what happens if you apply this to general relativity? And I mean, again, it's a complicated historical story. There's lots of work was done by Peter Bergman and his group. Earlier, there's also, I mean, I think quite important work on the Einstein-Hamilton-Jacobi equation by Perez. But this all led to the kind of seminal work of DeWitt and Wheeler towards the end of the 60s with DeWitt's most famous paper with the derivation of the equation in 1967. It's quite an interesting historical story about how he got to the equation, there's a meeting in the airport and all these different historical facts which are very quite fun. But the long and short of it is that they ended up with this picture of the world where the equation that they derived by applying the Dirac algorithm to general relativity is a time-independent equation. And that's the kind of starting point for this idea that time has disappeared in quantum gravity, and then we need to somehow get it back. And I love this quote from Wheeler. The time ordering events is a notion devoid of meaning. The concept of space-time and time itself are not primary but secondary ideas in the structure of physical theory. These concepts are valid in the classical approximation. However, they have neither meaning nor application under circumstances when quantum geometric dynamic effects become important. Then one has to forgo the view of nature in which every event, past, present, or future, occupies its preordained position in a grand catalogue called space-time. There is no space-time, there is no time, there is no before, there is no after. The question of what happens next is without meaning. I mean, I'd love it if people still wrote like that. It's a bit wonderful. So, I mean, I've kind of told you a bit of this story. Let me just give a little bit of hedging in two dimensions. The first dimension is that the equation, in some sense, that's written down isn't really a mathematical equation. It's not properly well defined. There's factor ordering ambiguities. There's problems with definition of the Hilbert space. There's lots and lots of stuff about the Wheeler-DeWitt equation that you could say, and ultimately this necessitated more modern, more sophisticated approach, including like loop-based approaches. It isn't the final story on quantum gravity by any means, and it's, even in modern terms, difficult to write down a fully well-defined Wheeler-DeWitt equation for quantum gravity. It's a kind of informal heuristic equation where we apply the Dirac constraint quantization algorithm and we get something that we can kind of interpret as something that stands for an equation of a quantum universe, but is not fully rigorous and well-defined, and it's not a theory in a kind of like really solid sense. That's the first thing. The second thing is that actually, in fact, for those of you who know any of my work, I don't in fact believe that the Dirac constraint quantization algorithm should be applied in this way to general relativity. I've written quite a lot of papers with Sean Gribb over the last decade arguing this. So in some sense, for this talk, you just have to assume, or I'm kind of pausing my own particular perspective on the equation just to investigate the consequences of pursuing this viewpoint. And I think it's been quite an interesting exercise for me to like put on someone else's coat and explore like the opposite position to what I usually do. So they'll just assume the Wheeler-DeWitt equation is well defined, and just what I really want to do is look at the particular structure, not of the Wheeler-DeWitt equation full stop, but of an incredibly simple reduced model where you kind of use a truncation of general relativity. You write down an equation that is a bit more mathematically fully well defined. We can solve it, we can explore the solution spaces, And that's the story I want to investigate and see the consequences for the idea of the emergence of time more solidly. How long have I spoken for?
45 minutes, roughly.
I've spoken 45.
No. I mean, you usually have 30 minutes.
Okay, great.
Yeah, sorry.
Perfect.
What's your 2024 citation?
That is, I mean, slightly less optimistic than my Chris and Nick. That's the book with Sean, which is.
There is no after, there is no.
And so the book with Sean will be called Symmetry and Evolution in Classical Mechanics, and it's the first part of our series of books now, which has expanded out into arguing that there is time in quantum gravity. But I mean, if you wanted something that's actually published, we have a PLB paper arguing that we should get time in these kind of quantum cosmological models and exploring the consequences. I'll talk very briefly about that with a bit of advertising right at the end. Okay, right, so let's look at an actual equation, right? So imagine the universe consists in a single geometric degree of freedom, the scale factor, and a single matter degree of freedom, a scalar field. It's a nice, simple universe. It's homogeneous, isotropic, finite dimensional, but we still have some kind of simple finite dimensional version of the Friedmann equation. So it's not unphysical in the sense that at a very aggregate level describes something a bit like our universe, and these kind of very, very, very like general variables. And we have some of the features of cosmology. In particular, we have things like singularity, we have expansion of the universe. Not in this case, but in general, you can put in dark energy as well. So we have this simple universe. We use a variable transformation where the scale factor is related to this alpha variable. So when you see the alpha, you can just read it as a kind of natural logarithm of the scale factor. Crucially, we also have a Planck mass in this equation. So if you look at the form of the equation, this is the overall Hamiltonian, which we got from the Dirac constraint quantization algorithm. This is the wave function, which is just a function on the geometric variable and the matter variable. And then we have a kinetic term associated with the geometric variable, and then a kinetic term associated with the matter variable, and then some kind of messy, horrible potential terms there. Okay, so it's still a fairly difficult equation to solve, but it's much, much simpler.
K there is +1, -1, or 0? Is that the...
Yeah, exactly. So the spatial curvature is the K, which is just the signature. Thanks. So what Kiefer proposes is that we can derive an internal clock, and this is a kind of very natural structure, or kind of popular strategy, which I mean goes back quite a long time, is that we take the equation, which itself it doesn't have any time variable. This is a kind of h psi equals 0 time independent equation, and we try and use one of the variables that we do have as a clock variable, and then kind of recover time evolution with respect to a physical variable that plays the role of the clock. The idea, or in a kind of general, in a simpler models, we can do this without having to do some of the semi-classical moves. But in this particular model, we actually need to be able to take a semi-classical limit to make this separation. To be able to do this, what we'll need to do is neglect the coupling between the clock degree of freedom and the dynamical degrees of freedom, at least to some order. And so, in some sense, what we want in a limit is that the classical degree of freedom, the clock degree of freedom starts to play something close to the role of a classical parameter that can label successive quantum states of the matter degree of freedom. So we're using one part of the dynamics to be a clock for the other part of dynamics. In that sense, the chrono-ordinal, chronometric structure is being derived from an equation which is fundamentally no temporal structure to start with, at least in the relevant sense. And this is possible in this case. if we choose alpha as the clock variable, specifically because the very large value of the Planck mass means that we can do a small parameter expansion. So this term here is is used as a small parameter, and then take alpha to be fixed as a complex number parameter rather than a wave function variable. And then
What exactly does it mean to say that the mass Planck is large? It's large, I mean, it's a dimensional quantity, so it's large. In what sense?
I think it's large. This term here is large relative to the other terms.
But being dimensional, it's hard to see how what exactly you're saying. I mean, I don't work with units in which it's a mass Planck equal to 1.
I mean,
It's choice of units, so what? Perhaps I'm not understanding.
I mean, presumably the scale factor, you can say the scale factor is large compared to the Schwarzschild radius defined by the Planck mass.
The scale factor is 1K series of
I mean, I think at this level it's really that you can do this particular expansion for this equation, right? Like it's not, I think, like.
Or perhaps the ratio between the mass Planck and the other mass.
I mean, so we'll come to this later, right? I mean, so this technique is really originated in the context of molecular quantum chemistry, and there the expansion parameter is dimensionless. And so there it's actually the ratio of the nuclear mass to the electron mass. I mean, in the paper, Kiefer does point out this disanalogy in terms of it being dimensional. I have a really strong answer why it won't make a difference. But so I mean, thanks. So I need to think about that more. I mean, the other obviously there's G's and C's that have been set to 1 here, right? Where have we gone? Okay, so the idea is that you can then take this particular approximation scheme where you define for each value of alpha, which is now playing this kind of parameterizing role, you define this reduced Hamiltonian where we're not including the kinetic term. And then we define this eigenvalue equation for the reduced Hamiltonian, which gives us these families of eigenfunctions for each value of the parameterization. And so then the important fact is that these families are such that they vary very, very slowly with respect to the parameter. I don't have a whiteboard, unfortunately, but you can imagine, I'll show a picture later, there being parameterized families of these eigenfunctions which don't vary very much as you move along in the alpha parameter. What's important then is that the equation we started with, 1, we can make an ansatz for it such that we can separate out these eigenfunctions of the reduced Hamiltonian from a part of the wave function that just depends upon the geometric variable. And then in the appropriate limit, the idea is that because we get this slow variation of the eigenfunctions, we can neglect the variation of these phis with respect to the alpha variable. So it's essentially a way of using the kind of structure of the different parts of the Hamiltonian to formulate an ansatz, and then in a certain limit, you can then separate out the equation and have a simpler form. It's exact up to this point, and then we take the kind of interaction between the geometric degrees of freedom and the electron wave functions, these kind of parameterized, sorry, not electron, matter wave functions, there's going to be electrons in a second, to be such that they're kind of effectively decoupled. The long and short of it is that we can end up moving from an equation of this form to an equation of this form, where we now have a simpler kind of dynamics that we can use to solve for these C's, these bits of the wave function that only depend upon the geometric variables. And then we apply another approximation, a WOKB approximation, which is basically saying that we're in some semi-classical limit where the wave function's peaking around the classical trajectory. The wave function, the part of the wave function rates the geometric degrees of freedom. And the net result is that we end up having this kind of semi-classical derivation of a temporal equation, or equation with an internal temporal parameter, by first taking this approximation scheme where we can neglect these terms here, the variation of that part of the wave function with respect to the parameter. And then second, we have this kind of simpler equation which we then solve in the limit where the wave function is appropriately peaked around the classical variable. So we have an approximate process to deriving a diachronic equation for matter in which the internal degree of freedom, the alpha geometric degree of freedom, is playing the role of a clock. And as I kind of implicitly have been saying, once you start thinking about this way, it's difficult to stop. The first approximation scheme really comes from the Born-Oppenheimer approach to molecular physics, where the gravitational degree of freedom alpha is playing the role of the nucleus. And we think about the alpha parameter as kind of being like the fixed nuclear position, which is, again is like a kind of we don't consider the variation of the electron wave function for different parameters, or it's like the relative variation of the electron wave function for different values of the nuclear parameter is assumed to be very slow, or very low. So again, in this context, it's about relative size of different parts of the Hamiltonian again. We also have this structure where we have a kind of kinetic term for the nucleus, and then we have a kinetic term for the electron and a potential term. And in this case, it is a dimensionless parameter, a small parameter expansion. And the cogency of this has been criticized in this 2021 paper and also in Craig's 2017 book. And I'll come back to some of the criticisms and how we should understand, or how I think we should understand them in a little bit. What's quite interesting is that in this case, in fact, for this model, the WKB approximation isn't valid for all regimes of the alpha parameter. We actually find that the wave packets, if their evolution with respect to the internal clock, spreads out from the classical trajectory under this late time boundary condition, where we have alpha going to infinity. So the validity of the semi-classical approximation, in fact, can be evaluated within this scheme, and in fact fails for certain kind of limits in this scheme. And I mean, I think in particular, if those of you might be wondering why I'm talking about this in a conference on the arrow of time, we haven't got any directed temporal structure at all yet. This is the kind of diagram of the spreading. This is actually where Kiefer, in his earlier paper and also in his book, and also, I mean, Zeh talks about this as well. It's precisely in this regime where the WKB approximation breaks down, the wave packet stops bunching around the classical trajectory, that Kiefer argues that we actually have to bring in an environment. We have to bring in other degrees of freedom. And then we get to this point where we're like, well, what on earth is the environment in quantum cosmology? And I mean, I think this is a quite interesting and instructive example where the environment is endogenous. Really what we're talking about when we're doing quantum cosmology is some kind of macro, coarse grain, like bulk type variables, more like a fluid almost, right? I mean, they essentially are like hydrodynamic equations. And so the environment is then the inhomogeneities, the fine-grained degrees of freedom. And so what Kiefer argues is that we should understand the breakdown of the semi-classical limit as requiring us to think about other degrees of freedom. And what he does is, he's got an explicit model trying to do this, where you introduce these endogenous environment in terms of inhomogeneous degrees of freedom. And we have a kind of Wheeler-DeWitt equation. We're now just focusing on geometric variables, not worrying about matter at all. For our alpha variables that we've been talking about already, these kind of coarse-grained hydrodynamic variables, but then also some fine-grained variables, which we'll use a little xi to represent. And then we have some form of the potential, which is asymmetric about the alpha, which is playing the role of the clock. So the potential goes to 0 as alpha goes to minus infinity. If you remember, alpha is log to the base e of A, so this corresponds to the Big Bang, right? To the early universe. Scale factor is going to 0. And what Kiefer and Zeh propose in this, maybe it's not in that paper, anyway, but they propose at various points, is we put a boundary condition on the wave function together with this potential such that we get this kind of simple product state structure again as we go towards the Big Bang, as we go to the kind of alpha goes to minus infinity regime. And so what we then have is a kind of way of, given this condition, deriving an hour of time. In particular, what they propose is we take the dynamics of 6 combined with this simple boundary condition, so this dynamics of this condition, to be such that, or we can show it will be such that, for increasing alpha we get increasing entanglement between alpha and the other modes, and then what they propose is we interpret this in terms of increase in entanglement entropy with reference to a subset of relevant degrees of freedom, where we can then coarse grain and get a kind of density matrix, reduced density matrix for the reference degrees of freedom in the alpha, and then we have an entropy measure that we're increasing with increasing alpha. So we've now got all the way from starting with no temporal structure at all, using these limits, Born-Oppenheimer type limit, WKB type limit, and including other degrees of freedom, and doing this coarse graining operation, we then have a kind of framework for thinking about chronoordinal structure, chronometric structure, and chronodirected structure within the kind of resultant system of equations.
But having chosen that particular boundary condition at alpha close to minus infinity, and you by hand putting...
I mean, literally to a word, this is where we'll end up in the talk, because I agree. So I mean, that's the point, right? Well, how cogent is what we're doing? Does the approximations, what legitimates them? Where is this boundary condition come from? I think we need to do more work to show that the story of the derivation is fully consistent, fully explanatory, and I think that's one of the really important roles that philosophers of physics can play. It's just this kind of keeping the physicists honest and checking their assumptions and checking their story. And so in this very interesting paper, no time for time from no time. Just about managed to say that correctly. Eugene and Craig. I mean, I really do recommend the paper. It's very short. It's very readable. They say the following: programs in quantum gravity often claim that time emerges from fundamentally timeless physics. In the semi-classical time program, time arises only after approximations are taken. Here we ask what justifies taking these approximations and show that science seems to seek in when answering this question. This raises the worry that the approach is either unjustified or circular in deriving time from no time. So I think this is a really nice challenge, and it's definitely something that I don't think the physics literature has fully clarified how these limits work and how this story really is deriving time from no time. And I think there's a lot of interesting stuff to kind of build on here. So I mean, I'm going to take a little bit of liberty, I hope you'll forgive me, with the dialectic, and just chop things up slightly differently. And I'm really, in some sense, engaging with my reconstruction of Chiao and Callender as much as the specific arguments, but I think the spirit is hopefully going to be the same. So we can chop up the challenge into two parts. incoherent assumptions, arguments for semi-classical emergence of intrinsic temporal structure from the Wheeler-DeWitt equation assume the existence of extrinsic temporal structure. So it'll be a really, in some sense, serious problem if we're deriving time from no time by adding in time. It's not quite clear that what we're doing is showing the emergence of time. We're just showing how you can put time back into a timeless equation and get time, which doesn't seem to be very impressive, is perhaps incoherent. That's the, I think, really worrying charge, and I'm not sure this one goes through. I'm not sure. I think the one that's less worrying but more of a worry, in that I think it's got a lot more teeth in this case, in particular with regard to the arrow of time stuff that I talked about, is really that this is not showing, and to some extent with the WKB one, it's not showing that why. I remember we talked about explanation and physical salience of the approximations earlier, that these derivations aren't showing why time emerges. They don't explain why time emerges. They just allow you to derive time. It may be consistent, but it's not explanatory and it's not really enough to explain the emergence of time. And I've got a lot of sympathy for this, that way of structuring the objection. So I can kind of again chop up the arguments, and I'll kind of slightly change one of them. Again, please forgive me. As follows. So for argument one, dodgy analogy. The Born-Oppenheimer approximation uses mass scales as proxies for time scales. Application of the approximation thus either makes implicit use of time scales or is unjustified. I think I have a response to your worry, and I'll come back to it. So, I mean, there's a real problem, right? We're using these mass scales as a really important part of justifying the approximation, but if they're really just being used as stand-in for a time scale, then it's not clear that we're deriving time without assuming something about time. 2, temporal smuggling. The WKB approximation uses classical momentum variables, but classical momentum depends upon time. Therefore, we can't justify the use of these approximations without smuggling in extra temporal structure. I think this one is the one I'm in two minds. I'm close to thinking is a more serious problem than I maybe have in the slides. Third and final, negligibility. The application of decoherence involves ignoring small terms in the reduced density matrix, which is unjustified without observers, but the existence of observers requires both time and decoherence. So there's a real problem about the explanatory kind of structure about what's going on. Let's go through them. Before I go through them in turn, this is particularly due to Nick. One mode of response is just to kind of step back a bit and say, well, ultimately the proof of the pudding is in the eating. If we can derive these structures, isn't that enough to justify what we're doing? We get the right result. We end up, I didn't talk about that much, but we end up being able to get semi-classical FLRW. We get something like the Einstein-Perez equation. We get an arrow of time pointing away from the Big Bang. We get the right kind of structure, at least up to this WKB breakdown point, which is more speculative, which I'll talk about in a second. And interestingly, Born and Oppenheimer actually say something a little bit like this in their original paper. They say, we develop all quantities with respect to small changes in a parameter x. We presume that the domain of oscillations is such that x is close to 0, and assumptions which is only justified by its success. So there's this kind of idea that you can say, well, look, ultimately we get back something that the result we want, so that whatever approximations we've made must be justified. So I mean, I don't know. I mean, to some extent, maybe this helps with the incoherence objection. It really doesn't do much for the merely self-consistent objection. And so I think it's one option, but I'm not sure it's fully convincing. Okay, so let's go back to the arguments and look at them one by one, and I can give you my read on it. So the Born-Oppenheimer approximation, and in the CNC paper, a lot of what they do is give the characterization which is given in physics and chemistry textbooks. which, I mean, it's actually difficult to find a more detailed characterization. Nick and I spent quite a lot of time looking. And that, in these books, often what people talk about is the time scale of nuclear motion versus the time scale of electron motion. But actually, in the kind of mathematics, and particularly the more rigorous treatments that we've found, it's really about the relative size of the nuclear kinetic term, the Hamiltonian, and this ability to do this approximation where the wave function splits into these eigenfunctions that aren't overlapping and have non-negligible partial derivatives with respect to the position variables. And so, I mean, just going back, I think the key thing and the way of getting the dimensionality out is the size of this eigenvalue compared to this term here. I think that's the key like kind of formal way of in both cases, the molecular case and the quantum gravity case, parametrizing the validity of the approximation. And what you can show is that in these situations where we have this mismatch between sizes, you get these families of non-overlapping eigenfunctions, and you can justify neglecting this partial derivative of the bit of the wave function that describes the mass degree of freedom stroke electron with respect to the geometric degree of freedom stroke nucleus, which is treated as a classical parameter. And so I think this stuff is in need of justification, but I think the justification can be done without any extrinsic temporal structure. And what's interesting is we can't do it the other way around. We can't apply a Born-Oppenheimer approximation that will work for using the matter degree of freedom as the clock for the geometric degree of freedom, or using the nuclear wave function, or classicizing the electron wave function and not the nuclear part. So there's a weak sense, perhaps we can call it a how possibly sense, that it's explanatory because it gives us a sense in which time can emerge from one choice of internal clock, but in this model it's not, we can't do things the other way around, which isn't always the case in these style of models. Anyway, so this is the kind of diagram of what happens when things go wrong and we get these regimes in which we have overlapping eigenvalues and the approximation can break down. Here and elsewhere there's a very, very nice mathematical physics paper by someone called Jekko from 2014 which goes through a lot of this stuff in, I mean, kind of really like mind-crushing detail. Okay, temporal smuggling. Like I said, this is one I'm perhaps a little bit more worried about than the first one. So the WKB, we do invoke classical momentum variables. I do want to say, though, that in the context of classical momentum variable is the canonical momentum, not the Newtonian momentum. So it's not clear how temporal it is. Maybe it doesn't have extrinsic temporal structure, in some sense at least. But we do have to assume we have tangent vectors and cotangent vectors. So there is some temporal structure in the whole idea of tangent spaces. But it's not the same as having a parametrized flow in a Hamiltonian, in a genuine Hamiltonian theory of a non-zero Hamiltonian. We're not dealing with a phase space where in this framework, I in fact don't believe of what I'm about to say, but in this context, we don't deal with a theory in which there's a genuine temporal flow in the phase space. If we think about things in a kind of standard Wheeler-DeWitt type way of thinking about time, because the Hamiltonian zero, and we treat it to be generating a transformation that doesn't change the physical state, to use Dirac's terminology. So it's not, I mean, also moreover, like, we don't really, we get out the Einstein-Paris equation, but we're putting in some of the substitutions for how we understand the momentum variable and how it relates to the quantum variable. So it's not quite clear we're explaining the ability to get the classical dynamics out of the equation. That said, I think we don't have this problem with incoherence. I'm not even sure we have necessarily a problem with circularity, because we can talk about how, as I said, how the approximation breaks down. In particular, what we can do is really just talk about the structure of functions in a space. This is phi, this is a, so we've gone back to the other variables. And these are wave functions, and we can ask the question, does this follow the classical trajectory in a phi space? We don't have to talk about classical trajectories with temporal structure. We can talk about, in the space of relative variation between classical variables, put a wave function in that space, and does the wave function follow the classical trajectory? If yes, then the WKB approximation should work. And so there's a sense in which we can have an atemporal validation procedure for the approximation without kind of slipping into this kind of dodgy double standards problem. Okay, so I mean, I've been agreeing with David far too often in the last few years, so I just put a slide in to disagree with David a bit. So let's talk about the negligibility problem. And so this has kind of come from inspiration with I think fairly interesting debate between David and various critics going all the way back to Zurich, but including Baker and Kent, about a particular argumentative structure in David's approach to probability in Everett. I mean, from my kind of 10 cents is that I don't think that's really the problem. It isn't circularity. I think if it was, the challenge isn't really that strong if it's circularity, because it's a consistency. The fact that in the decision theoretic Everettian approach to probability, you have a consistent package with the decision theoretic bits and the decoherent bits doesn't seem to be too much of a worry. I've written a paper with Richard David in which we argued really the problem is incoherence. But that's specific to the decision theoretic kind of approach. And so I think for me this particular problem, there's a disanalogy, and in the context of the Wheeler-DeWitt cosmology, what we can do is just modulo a solution to the measurement problem, give a consistent description of creatures like us who understand the world to be semi-classical and temporal. We can derive creatures like us within the wave function. And I mean, of course, someone then says, why are we, what justifies the particular way you've dealt with probability? What does that mean in the context of the wave function of the universe? You get sucked into the measurement problem. I'm not saying that isn't a problem. But I think so far as it goes, there isn't really a fundamental inconsistency in this approach, that if we hold in bracket, use your favorite solution to the measurement problem as you like, we can get, given that we accept that solution to the measurement problem, a consistent story about what's going on in this kind of semi-classical derivation, semi-classical plus decoherence theory derivation of classical-like structures from within the wave function. So I'm not sure there's a new problem. If there is a problem, it's just the measurement problem. Okay, so finally, how long do I have? Am I over time now already?
We are real time.
Okay, I have only a few slides. So, I mean, really the point that was made earlier, which Price in his wonderful 1997 book makes specifically about Hawking, haven't we just put the asymmetry in by hand? Hawking hasn't shown that, this is in No Boundary Proposal, he hasn't shown that asymmetric universes are a natural product of symmetric theory. On the contrary, he seems to have simply assumed the required asymmetry by taking the boundary condition to apply only to one end of the arbitrary universe. This amounts to putting the asymmetry in by hand. To what extent do Kiefer and Zeh make the same kind of mistake or have the same kind of argumentative weakness? I mean, it's interesting. On the one hand, the specific structure of Price's argument in the book doesn't seem to quite apply, because he really focuses on the problem for Hawking in justifying universes which are ordered at one temporal extreme and disordered at another, given time-symmetric laws, and also the problem of labeling one end the initial condition rather than the final condition. But in our case, we've got a very different structure. We don't have time-symmetric laws. We have atemporal laws. we have an asymmetry with respect to alpha in the form of the potential, but this is actually, in some sense, a spatial, or it's an asymmetry in a dynamical variable, not an asymmetry in time. The condition we put is not really an initial condition in some sense, it's a boundary condition on the variable. Moreover, what Kiefer and Zeh actually do is really what Price is saying Hawking should do in a quite mathematically similar model, and it's a shame Price, I think is aware of this, is that actually what they end up doing is constructing a quantum cosmological universe that has the feature that he wants, which is that the order is directly connected just to the size. So the arrow of time does reverse, and that we get a recollapsing phase in this model. And so what we get is a chronodirected structure that's not even always well defined when the universe is large, and then switches around as the universe shrinks again to the big crunch. This is from Kiefer. There doesn't exist a classical connection between different legs of across the turning point. There's another quantum region for very big values of the universe. I'll give you a little diagram to kind of show you the idea. Is that so this is the Big Bang, the universe expands. We get this WKB limit breakdown, classical limit breakdown here, and then we get some reverse kind of collapse with the arrow of time pointing again this way. I mean, I think what Price would particularly like is that creatures like us on either side wouldn't know which universe we're in, because we look this way anyway. What's interesting that we also not only get the emergence of time, therefore, we also get the disappearance of time, twice, in fact. Once here, where the classicality breaks down, and once here, where we get this kind of return to a Planckian regime. So symmetric treatment that we have, it gives time an equal opportunity to disappear during the big crunch. So we lose time once more. So ultimately, I mean, I'm not really happy with the Kiefer-Zeh approach for the very simple reason that there's no physical justification of this boundary condition. It seems to be just put in by hand, and as much as it doesn't seem to run into the problems that Price raises for Hawking's particular approach, it still doesn't seem to be satisfactory explanatory in particular. Moreover, we're going to have to look behind the confines of Wheeler-DeWitt cosmology in any case, because if you, like me, you think that we want to resolve singularities, we need to use alternative approaches, most famously loop quantum cosmology, but also other approaches that I've worked on myself. And so I mean, I'll just give you a very brief précis of the stuff what I think we could do instead. Some very interesting stuff on scale invariant dissipative cosmology, where we get measure compression, we get contact dynamics. That's a different way of thinking about the arrow of time in at least classical cosmology. Particularly Dave Sloan's written some really wonderful work on this. What I'd be quite interested, I've been working with Sean Gribb on a way of a non-Wheeler-DeWitt approach to quantum cosmology, where we use the canonical conjugate of the cosmological constant as a clock. We've shown that gives non-singular bouncing cosmologies for simple models. If these two things are combined, we might in fact not at all have a story about the emergence of time. We might be able to have a physically consistent model which we keep time in quantum gravity, and we have directed in a certain sense and kind of chronoordinal and chronometric structure kind of ingrained into our quantum gravity equation, which would then mean we wouldn't need to derive time. So just to give you three possibilities that one might have for a cosmology in the arrow of time. This is the one we talked about. This is the Kiefer-Zeh model, where we get a reversing universe with the arrow of time flipping. We can also get epikairotic universes, where we get an arrow of time with a big crunch and a big bang, but there's always entropy production. And Turek and co-authors have written about this. What I quite like, and what really fits with this kind of Julian Barbour scale invariant framework, is this idea of a Janus universe, where we get a bounce, but the arrow of time always points away from the kind of singular or the deep quantum cosmology regime. Thank you very much. Sorry I've overrun.
Okay, we have some minutes for questions, comments. Yeah, David was.
I want to worry about the idea that there's really a difference between what's going on in the average interpretation and what's going on here. I mean, not just that I think they're analogous, because I'm not clear why they're not the same thing. I mean, so firstly, you say pick up the third solution to the measurement problem, but it better be a unitary, no traps, no hidden variable solution, otherwise you'd be going in a different kind of direction. And in that, and specifically, it better be a unitary, no traps, no hidden variable approach of the kind that says what we're going to do is extract through the machinery of decoherence a family of quasi-classical branches where we will then treat the mod squared amplitudes as probability under the idealization that the cross-branch interference can be neglected. And we then, if you consider the family of such, I'm not necessarily granting that that family contains more than one member, but if one grants the family of such viable interpretations, the measurement problem is going to come down to how do you want to think about this ontologically, and how do you want to justify interpreting the mod squared amplitudes as probabilities under that idealization. I mean, why isn't that precisely the start?
So maybe I went through it too quick. The idea wasn't there was a disanalogy at that level. The claim was there's a dialectical disanalogy. If you imagine for a moment you agree with me and not yourself, which may be difficult, or me and Richard, not yourself, the idea is that the worries that we have about your use of decision theory, if those were the problem with the kind of package, in this context, that's not really the relevant issue. So I didn't disagree with you. I think at the kind of level of the detail, I think the point is that, I guess, do you see the point now?
So I'm not sure I do. I mean, the general setup is that any of these kind of approaches are going to break into two steps. There's going to be a justify the use of decoherence to pick out a collection of branches, and then justify, and then under the idealization that cross-branch terms are zero and decoherence is exact, justify why under that idealization mod squared amplitude, which has the formal properties of probability under that idealization, has the substantive properties of probability. Now, obviously, it's perfectly possible to say that given justification of that kind, differential otherwise doesn't work. So it's of course there are perfectly respectable objections to decision theory program, even under that idealization. But I didn't take you and Richard to be advancing simply a criticism of decision theory granting that idealization. I took you to be an objection to the package, and I'm not seeing how that could go through in a framework that doesn't generally deny access to the idealization where we're allowed to neglect that cross-branch interference.
So I'm not sure I understand that. I mean, ultimately, what I'm saying is that there's no new objection to this approach then to the question about how we should interpret decoherence. And that if the problem that Richard and I pointed to is a real problem, it's not clear that it's directly relevant here, unless you wanted to include the decision theory framework into this.
Yeah, thanks a lot for that. Yeah, I really like the this sort of derivation. So when I had it in the back of my head since I was a graduate student, because Thomas Banks had it, and I always thought it was the most beautiful thing. But then, yeah, I just think if we, I need to look more at your responses about the Born-Oppenheimer and the WKB, and also I think there are other ways I could extract the time stuff from the WKB than I did in the paper. But if we just sort of step way back and just think, but it's just really kind of simple thought where we just thought, if I were giving you a physicalist theory of consciousness, and so we had a theory, we interpret the theory, here's all the physics, here's all the terms, what they mean, and then I said, well, consciousness arises in some sort of approximation, and say, well, what does that approximation what justifies it, and then you say, well, to conscious observers, these things will look close or something like that, then it seems like it wouldn't be that satisfying. And it seemed like we were always getting kind of time scale type stuff justifying the particular approximations again and again. And so I'll just say, about the sort of, I think it's sort of Nick's response or your response too, this sort of all at once picture. I think that doesn't really make sense if so because you need to justify the approximation. So the approximation is not. So I have the fundamental theory. I interpret that all at once, and then now I get to work with the approximation. And then if I have to bring in all this other stuff that's not there in the fundamental assignment of the interpretation of all the fundamental quantities in the theory, then it does seem like cheating to this kind of all at once picture, because I could have, if I'm allowed to do anything, with my approximations, then I can get anything.
I mean, I think maybe we could think about the hard problem of time and the easy problem of time. So I mean, I don't know. I think it's in some sense a question of the burden of proof, right? Like, what do we get to assume to start off with, right? If we can assume what structure we have in the empirical data of cosmology, physics we have around us, and some timeless equation, and we have some procedure for deriving the kind of appearances from the timeless equation, I think there is something to say that what we've done isn't cheating. But I don't think I disagree. I don't think I agree with you fully. But I do completely agree that if that's all we do, then what we've done is not very explanatory or insightful. So I don't know whether your worry is more that we're really doing something downright inconsistent or illegitimate, or we're doing something that isn't really explain the fact that we started off trying to explain. It just shows how we can derive it in some way. So they seem to me two different objections, and I want to push back a bit on the incoherent, the kind of downright inconsistent one, but I really feel the force of this isn't really explaining what's going on one.
Yeah, I have a follow-up by her, but also
just to contrast it with, so when you've got your theory, you can put your interpretation assignments however you like. If you want to just call whatever time, call it time. But that's already now been done, and they said there's no time. So contrast that with, say, I take a different approach where it's not a semi-classical, where I just say that let time be defined by the phase of the wave function. Then time will be, there'll be some solutions where you have it, some solutions where you don't. So when you do wave functions, then there'll be no time. And then in some sense you could say this emergence, because not all the solutions of the equation have time. But you don't have like emergence sort of, imagine like horizontal versus vertical or something.
Yeah.
And then then I think that's not cheating, because you said, well, time is the phase of the wave function, and you have it. And so then that seems to be like not cheating. The other one, then there's the remaining question about whether it gets smuggled in or not. But if it does.
I mean, I like not to talk about time versus no time. I want to talk about levels of temporal structure. And I completely agree that there's some implicit temporal structure to start off with in this way of thinking about internal degrees of freedom, and in these hangovers from the classical concepts of conjugate variables and blah, 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 blah. So I agree that there isn't time from completely no time. What I think there is like a very thin temporal structure to start off with in the equation and in the supporting machinery, and you get more out in some limit than you start off with. So I think there is something substantive. Yeah.
Well, I was just going to say on the approximation point, I mean, there was empirical motivation for adopting the Born-Oppenheimer approach. So it's not you're just plucking these limits from nowhere, right? So I feel like there's a confusion.
In quantum chemistry or in quantum gravity?
Well, so that the approximation has empirical grit in other contexts makes me think that it's not just that it can have some explanatory power in this other context. But I also think there's sort of a flipping of explanans and explanandum here, because what are we trying to explain? The fact that we have a temporally ordered or apparently temporal ordered situation here, right? So if you can get it back, I don't know, I don't, inconsistency isn't a problem because we have empirical evidence of the thing we're trying to see. So clearly we get to the thing we're trying to explain. I don't know if I'm making myself clear.
I mean, but if it really was, like, if the approximation wasn't actually justified mathematically, then had we got time out, this would be really wouldn't be convincing, right?
Sure. Yeah.
And I think that's the thing that I don't think is the worry, because it is there is a mathematical way of justifying why these functions have this behavior, which you can show through computer simulation or through calculation.
Yes. Yeah. I agree.
That the electrons that go really fast around the nucleus justifies it in this context.
No, I don't think you need to use the analogy. What I'm saying is you can use the structure of the actual equations to show that the levels are separated in this case.
Okay, we are out of time. Very, very quick. Daniel, would you be very quick?
Well, I don't know.
Do you think
It's
that
not
you are
quick, but
very
I will try to make it short than me. I think what is at stake here is, in part, whether this equation we started from is justified. If we take it that
Sure.
it was given by God and we know that this is the theory, then we could say, okay, and we know the universe is so and so nice that with this story and these approximations we can get. But since we cannot know that this story is true, and we want to be able to say, oh, look, you should believe in the Wheeler-DeWitt equation because, look, it produces a time for a universe. Then the test should be stronger. And I think one way of trying to see if we are justified in doing that is to take a very similar equation in which we know that the interpretation, we know what you can get and what is legitimate to get and then test applying the same kind of logic and the same kind of value. And I was thinking, take a two-dimensional Schrödinger equation and look at the, fixed energy solution. So now you don't have time. Set up a potential for your particle that looks something like that, and now repeat your steps. And I will tell you, I have obtained from a two-dimensional Schrödinger equation of a particle in a plane time.
But this is be done,
I
right?
would say that since we know that that's not time.
I mean, do we know that's not time? Right? Like Mott, in the 20s, Mott had a way of getting temporal structure out of a time-independent Schrödinger equation, right? And so we do know that there's a sense in which time-independent Schrödinger equations do encode temporal structure. So I think
I remove time. I'm going to look at just, eigenstate of energy E equal to that particular thing. There is no time in that equation. Absolutely no time. That's a timeless setting.
I mean, you have
of a stationary solution.
You have to have a certain level of complexity in the system, but there are procedures to.
I put some
Sure.
in my.
So what I'm saying is that it's not the true for any time-independent Schrödinger equation you can derive temporal structure, but that's actually kind of the point, right? There are some time-independent Schrödinger equations from which you have these Mott-type solutions where you get temporal structure from them. I mean, Julian Barber calls these time capsules. And so it is true that there's a way of thinking about condensed matter, real physical systems, and using time-independent equations to describe their dynamics. And so I think in your example, this does mean, like, it indicates that what we're doing isn't completely nonsensical. I actually don't believe in the Wheeler-DeWitt equation. I don't think the derivation of it is solid. And so from that, my actual kind of most of my work, I'll be arguing the other side that these kind of uses of Wheeler-DeWitt type equations to derive dynamics is a special case. There's physical reasons why we're able to do that. Really, we do need dynamical Schrödinger type, time-dependent Schrödinger type equations, and that's physically well justified. And in quantum cosmology, we should be using dynamical Schrödinger type equations. So I mean, with my hat of myself on when I'm doing my research, I really don't think this is the right approach. But with my other hat on, I think there is an interesting sense in which we can do these kinds of things in some cases to get time out of these timeless equations. And it's part of the problem of for someone like me who doesn't think this is the fundamental approach to explain why it works sometimes.
Okay, many thanks, Karim.